Students, in this session, we will be looking into modeling of electrical systems. Modeling of electrical systems is writing a set of mathematical equations so that the mathematical equations govern the operation of electrical system. Here, we have given a simple circuit of RLC which are connected in series with the supply. The supply is given the name Vi of t. So this is your input variable. We have taken Vi of t as the input variable, and there are three components: resistor, inductor and capacitor. We have taken voltage across capacitor as output variable. So we have given a name of V naught of t. So now we are going to find the transfer function of this circuit. So the output variable is V naught of t and the input variable is Vi of t. Now you have got to write an equation so that the equation governs the operation of this circuit. So we can use Kirchhoff's voltage law. So Kirchhoff's voltage law states that the rise in voltage is equal to sum of potential drops in a closed loop. So we are having a rise in voltage of Vi of t here. So Vi of t is equal to sum of potential drops across resistor, inductor and capacitor. So R into I of t is the voltage drop across resistor. L into di of t is the voltage drop across inductor. 1 by C integral of I of t dt is the voltage drop across capacitor. And since your output voltage is taken across the capacitor, so you can write separately V naught of t is equal to 1 by C integral of I of t dt. So now after writing the differential equation, please take Laplace transformation on it. When you take Laplace transformation on this differential equation, like V of t will become capital V of S. Because in time domain the variables are written using a small letter, and in a frequency domain the same letter will be in capital, and the variable will change from t to S. In time domain the variable is t and in Laplace domain it is S. So after applying Laplace transformation you get it as capital Vi of S is equal to, for R into I of t it becomes capital R into capital I of S. When you take Laplace on di by dt, it is actually S into capital I of S minus I of 0. But here we have not considered the I of 0 because we are assuming 0 initial conditions. 0 initial conditions means that now we have taken that there is no initial current through this inductor. There is no energy initially stored in this inductor. So that is what is the meaning of 0 initial condition. So we have neglected I of 0. So just after taking Laplace transformation on di by dt, you get it as S into capital I of S. So after taking Laplace on this term, you get it as 1 by C I of S by S. Here also we have neglected the charge, initial charge stored in the capacitor. That is, we have taken the initial charge stored in the capacitor as 0. So after taking this Laplace transformation, you get an expression like this. You can also take a Laplace on V naught of t. Earlier we told that V naught of t is equal to 1 by C integral of I of t dt. For that expression, when you take Laplace, you get it like this. So now you have two variables, that is the output variable V naught and the input variable Vi. So your transfer function is output variable to that of input variable. So just divide these two equations, you get it as V naught of S by Vi of S. So once you divide it, you get it as 1 by SC divided by R plus SL plus 1 by CS. You can reduce it to write it like this: 1 by S square LC plus S into RC plus 1. So now you have got the transfer function. So I think we have followed all the steps. We have taken the system. We have written an expression which is governing this operation of this system. We have taken the Laplace on the equation, that is the differential equation, and then we have appropriately taken the variable on the numerator and the input variable in the denominator, so that you get the transfer function. The transfer function is now given the name g of s. Here is another example where they have given the differential equation of the system straightly. They have asked to find a transfer function with 0 initial conditions. So when you apply Laplace on d cube y by dt cube, you get it as s cube into y of s. Similarly, when you apply d square y by dt square Laplace, you get it as s square into y of s. For this term, you will get it as s into y of s. For this term, you will get it as y of s. The input variable is u and the output variable is y. So here you will get it as s into u of s plus u of s. So I have taken u of s common. Since this is your output variable and this is your input variable, just bring it like this, y of s by u of s, you got the transfer function. So this is like we have done simple 2 steps to get the transfer function. This is another example of electrical system. This contains 3 components Rlc, but all the 3 components are connected in parallel to the source. Here the source is a current source, so it is indicated by I. The current through the resistor is given by the name IR. The current through the inductor is IL and current through the capacitor is IC. So now this parallel RLC circuit has to be modeled. So first we will write the Kirchhoff's current law for this, because you have a single node. So for this node you can write a Kirchhoff's current law. Kirchhoff's current law states that incoming current is equal to sum of outgoing currents. So it is I is equal to IR plus IL plus IC. So now I want the students to write a differential equation governing this particular system, and take IC as your output variable, that is the current through the capacitor as output variable, and take the input current as this I, and find out the transfer function. That is, you have to find capital IC of S by I of S. The clue is here. So you please write the input current equation, as well as you can write the IC current separately. So 2 equations you will get. After writing the 2 equations, you can take the Laplace, divide it, so that you get your transfer function. So I give this as a small assignment to the students. So we will meet in the next session. Thank you.